when you do that. Okay, so we can see over here, well, let me just say that if you're starting the video, sorry, we forgot to start the stream without you. We're talking about springs. Okay, so we're talking about a massless spring damper, and we can see that essentially what is going to happen is that the I guess if we have the object stretched out on the spring, the damper is just going to cause it to slowly go back in place, right? Should we program this? Kind of see what happens? Yeah, okay, good answer. Let's try this out. Okay, so we're gonna make an example 14 with the same thumbnail as all the other ones. Kind of get some practical experience with the library. So let's go ahead and add number 14. And I think let's find a good one to start off with. Let's go with the popping blocks one. So I think that's example 3. Okay, so we got something we can start off. Okay. So the two things that we want to draw are, so we have a rectangle there. I guess we can keep the sun in the background. New simulation. In this case, I just want 2 state vectors. So we're going to, inside of our constructor, and we can adjust our K. We can adjust our D value, and I think we can set where our mass is. Okay. It looks like this would be okay, let's just do that. Oh, our V naught too. this dot mass dot okay. Now we got to draw this out. So we got to set the world matrix at the first one. This dot wall dot I guess we could just put this in the middle. And then we can set the location of the mass to this dot mass dot x0. Just put it in the middle of the screen and then draw that. Okay, so let's see where we're. That looks good. Okay, so now let's find out what happens if we go ahead and adjust this. So let's see if we let's see here, x naught. Okay, and so xor.t1 is going to represent the number of seconds that the this whole thing has been running at. But we probably want to set we'll set a counter. This dot total time equals 0. And then what we'll do is inside the update function is to, if we reset it, okay. All right, so now we want to just let's do this first case where if the mass is 0, this dot mass dot x equals the whatever the initial position is. Interesting. Oh, good point. We should probably have like keep track of our own x naughts. Because we're using a fixed equation, essentially. All right. Start. Okay, so it's x naught times math.exponent minus this dot d over this dot k times total time. All right, so theoretically, Let's set it out to 10 and see what happens. Either it happens so fast or we're not doing it right. Oh. This is the challenge. When it does nothing. Okay. So let's debug it. Let me close some stuff first. So what do you think? What are we expecting this block to do? When we see it run, what do we expect this block to be doing? Because the first thing we're doing is doing a massless spring damper. Okay. So this is what, and this equation comes out of the fact that the mass was set to 0 before we could come up with an equation for it. Okay. So yeah, the first thing we're going to do is check to see if the mass is 0. We're going to find that out. We'll see if our equation is actually updating. Now, the way that these things are used in practice, how do we think that you're going to get from, I guess, implementing these equations? How do you get from just having one spring and one object? How do we think we get to essentially to balloon guy? How do we bridge that gap there? Okay, there's no errors. It's at 3.93. Okay, I guess that's. Oh, I have it. I know what's going on. Not using the graphics library, correct? There's no X not in there. So basically always passing 0. There we go. So this is what happens. So we throw it in there and it just slowly does its thing. Okay. So let's go ahead and not hard code this stuff so much. We have these HTML utilities here, get range value. This dot m and let's go ahead and add these to our create range row. Spring D. Oh wait. So controls, our ID is Spring D. Let's start out at 0.5. Let it go from 0 to 2. And steps at 0.1 or 0.5. Alright, this will be our spring constant. And this will be 0.5, and we'll go from 0.0 to 2.0. And our last one will be our mass. And we'll start this one off at 0. And it can go from 0, say, it can go up to 5 kilograms. And we'll just do steps at 0.1. Okay, let's see if this allows us to tweak the spring constants here. Okay, so if we set a high damping value, then we would expect this to like really slow down. And if it's got a very low, then it doesn't. We kind of make something nice and snappy. Now, what happens if we bump the spring constant? So they both can kind of play with each other in terms of the spring is like, it's like one of those really long loose springs, like, you know, versus like a really thick, heavy, you know, springs that you might see on a swing or something. They just hardly budge at all. Okay, so if we have a really slow, and let's think about it, what happens if K is low? Because it's written in terms of how far you are from the equilibrium point. What happens if it's like a restitution force? What do we think is going to happen if we set K to be low? No, it should be very. So if we set this very, very small, I guess we could set it to. Then it's like trying to push down on that spring, you know. Okay. Which is exactly what we're seeing here. Okay. So even though the damper, let's set this in the middle there. So that's essentially what's going to happen is you're going to get this exponential decay in the reaction of the spring. Okay, so this would be you can make it very stiff or very loose, but ultimately it's to slow it to a stop. Okay, it's going to slow it to a stop. Okay, so the next thing we need to do is, and this is exactly what we're seeing here, this exponential decay, until eventually it goes backwards, right? Or it gets to it plateaus to the value 0. Okay, so then the next kind of spring is a springless mass damper. In other words, we set K equal to 0. There's no spring, and we only have the mass and the damper. That's the only thing that's affected by this. Okay, so now we see we have velocity here. That's our initial velocity, and we have m over d. So that's kind of our new time constant. So let's see what happens with this one. I guess I feel if I get a little bit lucky, it'd be easier just to copy this. So a massless spring damper, but a springless mass damper. Okay, so in our update function, else if this dot k equals 0, then this dot mass dot x equals this dot x0 plus this dot v0 times this dot m over this dot d times 1 minus math dot exponent minus this dot d over this dot m. Go back here. Times total time. What's that?
The original definition.
The E, so the first one was basically minus k over d times t. So if we go back to here to our equations. Okay, so we have k over d. This time we have no k, so it's actually be m over d because it's more or less the same, or it's pretty close to the same equation that we're solving. Except that obviously we have a different, well, I say they call these a characteristic function. So, you know, if you want to prove that these equations are actually doing that, all we'd have to do is essentially take the first and second derivatives, right, of these functions, and then that should just look exactly like that. I mean, essentially. So I bet those e terms end up canceling each other out, and you end up essentially with those two equations. Okay. Okay, so let's see the springless mass damper. Maybe for sake of this makes this kind of stuff easier to test, I feel like. This dot m, this dot k. Oops. So we could actually go here and we could adjust this so that it's I feel like the closer you get it to look like a math equation, the better it's going to be for us. That already looks better, I think. Okay, so let's see what happens, see if it actually works. So loading this up, we have a springless mass damper, so we'd have to have some kind of mass. Now we got to figure out why it doesn't work anymore. Let's see if this dot k equals 0.35. Oh, must have had it backwards. D. I was thinking we could add okay, let's go up here. To spring D, spring K, spring M. Oops. So we'll say velocity. Oh, that might have something to do with it. Let's say it can go from 0 to 5. Okay, so our springs over here. Let's maybe give it an initial velocity. Seems like it's working. Okay, that works because we were expecting. Let K, let's go over here. Let's figure out why this is, K is 0.5. Spring K. I would expect that to, very interesting. K is declared, but its value is never used. Oh. Let's do that. Make sure we're consistent there. Okay, let's see if this should, I would expect this to work now. Shouldn't work at all. One more idea. Anybody see anything obvious?
It just seems like it's not coming through 0. When you set the range to 0, it's 0.
So spring K.
No, the min value. Yeah.
And it looks correct. Okay, so then over here, dmk x0 v0. Unless this is, oh, k, then d. K, d, m. It's not really necessary anymore because I'm just doing the same thing here. Okay, so let's try that out. That maybe that was our problem. Okay, so we set m has now got some positive value to it, and so let's see what happens. Does it work the other way around? Well, maybe we could do something like, if k is close to m over d, d over m, t. Well, let's keep going. I do want to see what the other ones do as well. So is this what your guys' experience in the homework is like? This is, I mean, this is like, I feel like this is the reality of it, because you know, you're working in any kind of like position, and this is the kind of stuff you have to deal with. This dot mass dot x. Okay, so the third case, and hopefully this will start working in just a little bit, and we'll figure out why that equation just is not cooperating. But the second one is the case where you have a damperless spring mass. Okay, and now we have a cosine in here. Okay, so what do we think the cosine is going to do to our, what's going to happen with our, yeah, we would expect it to be bouncing around back and forth. Okay, so we have this constant here, and we have a phase function in a missing parenthesis, but let's see here. So first we need to calculate the c value. So let's do that real quick. Let c equals math.square root. We have x0 times x0 plus m over k times v naught times v naught. Okay, and then c times the cosine of the square root of k over m times t plus phi. Now, what is that value phi going to do to our function? What do we think that phi is going to do? That's nice that one just worked out of the box. First try. What do you think a phi function is going to do? Yeah. Let me fix that real quick, because it's, where is it? Okay.
Just the temporal offset.
Over here, we have phi over here.
Oh, this looks like a phase offset to me. But
Yeah, it is a phase offset. And so where do you start on the cosine, right? Because cosine of 0 is, what's cosine of 0? 1, right? What does that mean? We're going to start off at the highest position, right? So if we set phi equal to 90 degrees, and where is it going to start off at? 0, right? Phi is going to start off at 0. So the phi allows us to decide where is our starting position at. Are we starting at the very beginning, stretched out all the way, or all the way to the end? What if phi is 180 degrees? Then where are we going to start? Yeah, the opposite side, fully stretched out. Okay, so phi allows us to kind of give an offset. Now, I told you, essentially, ignore the phi term just because we just want to see the oscillation happen. Okay, so we want to see the oscillation happen. And so we can actually see that here. This thing's bouncing around.
But it always goes back to its original.
Yes, always goes back. Because there's no, we have the restitution force of the spring, but we don't have anything taking energy out of it. So energy is conserved in this case. So, which I think is cool. This is maybe even a good introduction to what differential equations do. In some cases, depending on how you have the parameter set, you know, we have this oscillation where we got the cosine function coming in, or we have the exponential function coming in. Okay. So, all right, I think that's cool. Let's see if we give it like an initial velocity, what happens, and let's bring this back. It really shouldn't do, I don't know how much it'll do. Let's set it to a high number.
it's basically just making its wiggle room wider.
It's like saying that the spring is already traveling that way, right? That's what we're basically saying. The spring is already moving when we set it up. So if we give it like a tiny bit of velocity, we don't really see much. I wonder what the breaking point is right there. But we would expect the initial velocity to kind of expand the way the spring is working, right? How big the range is. So the normal range we would expect with no velocity. And in fact, if you noticed, watch when I restart it, that the spring will like basically be stopped still, and then it starts to accelerate towards the middle. So let's watch that. So you can see it's got that. Now if we add some velocity to it, then we should not see Okay, so now let's look at the last one, the spring mass dampers. Now we're going to put all of this together. Okay, so basically we see we have this value xi, which I don't think I told you what the value of xi is, but we have the calculation here. It's d over 2 times the square root of km. All right, I'm going to copy that. That looks like something that'll copy and paste well. Else, so this is our, if one of these other conditions are not met, then we'll say that is. Okay, so we have xi and those are t's. If I see x, it should be t. We also have another term, which is omega n. And omega n is I wonder if that was supposed to be 0.2. That's going to represent the angular velocity. I don't like this. I think there's an equation for determining the value of omega n. But let's see what happens here. So we stop here. Xi is a number. Oh. That's right. We have our scratch piece of paper out and we did nothing with it. Okay. What's that?
You said it's a dot x.
Oh. That was a typo. So we should expect to see some springy motion here, but then eventually settling down until it hits maybe we set the damping factor as well. Set that high. Not too bad. Let's look for I forgot the book at home. It's got the equation for calculating omega n. So let's see if we can find the whoa, okay. Let's go back up. So the zeta and this G is supposed to be trying to look at these oh, I know we can figure that out. Whichever one is inside the cosine is going to be the, so they have sine 1 over, or t over tau. too much suspension tuning in there. Let's oh. Okay. See what the mechanical engineers say. I'm just guessed that because I saw ME345. State equation. Okay, now there's another thing about the system being undamped, underdamped, critically damped, and overdamped. Okay, and that is, if it's undamped, then there's no energy loss in the system. So technically, it keeps going. So that's not realistic because everything has loss. Secondly, if it's underdamped, it's going to vibrate, but it's going to be basically, it's going to keep going until eventually it slows down and stops. That's called underdamped, in other words. If the goal was to have it stop before you got to where it needs to go, then it's underdamped. So that's where you get the oscillation in. If it's critically damped, then I believe that just means it's going to slow just at the right speed so that it comes to a complete stop when you want it to. And if it's overdamped, then essentially it's like whoop, it just, you know, gets slammed like slamming the door. That's like a overdamped system where the door stop basically brings it to a halt. So instead of having a nice smooth velocity, it's going to just basically, it's going to come in and then it's going to end up being stopped. Now the way that we figure this out is that if zeta equals 0, and so undamped means that there's no slowdown or there's no energy loss. Okay, so that's where we're going to have the E. Then omega D is omega naught, so whatever the initial velocity is. All right, and underdamped means that our zeta value is between 0 and 1. And therefore, because omega d is equal to omega naught times 1 minus zeta squared, this value is always going to be less than 1, and therefore our damped velocity, our frequency, is going to be going smaller and smaller and smaller and smaller. All right. Okay, so let's. And a critically damped, that's 1, suggests no oscillation, and hence no frequency. So in other words, it goes to a nice perfect stop. And if it's greater than 1, then we're going to end up getting, you have a square root of a negative number. So you can't technically use the system of equations to solve this problem because of that aspect. Okay, so think this, yep, Z, so this might be like our initial frequency, and I wonder, I believe that there is a way to figure out what that frequency ought to be given the initial like X naught and V naught, but let's just put in our this will change over time. Well, no, this should be just a fixed constant. Okay, so let's see what happens here. So we have all of them up. So we should see some damping in the system. This can be a challenge when you're doing simulation stuff because you're like, I want it to go fast. You know, you're like, what do I need to set my values to so that they're moving along. So let's start that to low damping factor. I think technically this might cause it to be I guess you could figure out at what point does this K or D cause this whole thing to be the different situation, right? So if we want to make sure that it's undamped or that it's critically damped based on the mass, then maybe you can't figure out, maybe you know what the spring value is, but you don't know the damping factor, or maybe you know the damping factor, but you don't know the spring value. Okay, so let's just solve that real quick. So let's find out how do we get our 5 kilogram object here? Like, what would our spring and our damping factor have to be in order for this to like work out? So I'm just going to use Z because I don't want to write it's a little hard to draw that simple. So we have D over 2 times the square root K over M. All right, so 2Z over, or I guess, we basically want to pick, we have 1 equals okay, so we need to 4 D squared K over M. So then 4M equals D over K. D over. Okay, so that means that if we can get 5, if we have D over K, let's just say that we want to set K equals to 1. All right. That way we just have something to work with here. So D over 4. So in order to get, so that's 5. Our damping factor would have to be 20. That seems high, but let's see what happens. Maybe we like underestimate, and this is another thing, maybe we underestimated the range of values that you know, we should have. So let's allow, I think I like that still. Let's set our defaults for the springs and the mass. Let's see, we have 5 kilogram mass. Okay, let's see what happens now that we can essentially set a really high factor for the damping. What's that? It might. Okay, so if we start, let's just start adding a little bit in there. Went over.
So at 20, it'll just stop.
It looks like this caused it to go unless we calculate that number out wrong. But if D was 20, then it would be Z equals 20 over 2, so 10 over the square root of 1 over 5. Sorry, 10 over the square root of 5. So our Z would be positive. Oh, you're right. Yes, it was a test. Okay, so 4K over D. If K was 1, we have 5 equals 4 over D, in which case D would equal 4/5.
D squared.
What's that?
Shouldn't it still be D squared?
Oh, yeah, D squared. Okay. Well, that would make sense. So in other words, square root of 4 over 5, almost 1. So I was thinking in my head the D's really should be 0 and 1. 1.5. Still needs to be high. Okay, so what do we think about springs so far?
Nail down to get some cool effects.
If you nail it down, you get some cool effects, yes. They're definitely interesting, but they definitely take a little bit of tweaking just to get right. You got to make sure the math equations are right. And then are we even throwing realistic values in, right? So let's see here. So there's that initial. For the over-damped case, there is too much damping in the system and it cannot get to 0 as quickly as the critically damped system can. I personally think of this system as sluggish. I guess maybe what that is like it wants to move faster, but it really can't. So anyways, let's look up spring values. What are some realistic constants for Hooke's law? I don't know if they have examples of springs in here. There's the harmonic oscillator, and that comes out from, we basically made one of those. Okay. We can look for some values a little bit later, but what I did want to mention is, so once we kind of got springs kind of mastered, then the trick is how do they work together? Okay, so right now we have like one end of the spring is fixed in space, but now what happens if you like connect springs together? What ends up happening to them? All right. I think in this case, right, you can kind of imagine, you know, if you hold one, like connect two springs, two different constants together, and we would expect them to be kind of like moving around in different ways. But that's exactly, oops, banging around over here. So the next step is then, okay, let's go ahead and connect these together into some kind of mesh. All right. And so the idea here is we got some, and we'll just put a damper. I'll just call it D, just for ease of use. All right, and then sometimes they'll put like springs in here. And now you're like in a case of, okay, I got to solve this, you know, one spring at a time, hopefully. And so now you have like, once you kind of got it nailed down for 2 points, now you got to figure out, well, how are they all working in concert with each other, right? And if you're only taking if you're taking a stab at it, I guess initially, then you either have to figure out what those values are supposed to be, or come up with a way of calculating what it is if it was already in its equilibrium position, right? So let's just say it could be fabric or a box or something like that, a balloon, where you can say, well, it's already the model is already consistent. You know, so if you blow up a balloon, you know, technically you could figure out what the coefficients ought to be so that the balloon basically maintains the shape that it's in. So there's an element of, you know, if you're using a surface, right? And these might be springs. Okay, but then maybe you have an object like a rubber compound or something, like a rubber ball or a rubber cube. And so then the trick is like, well, okay, how do I, you know, if I bounce something, right? If I, you know, like we got the bag here, right? Got the bag. And drop the book. So there is an indentation now where the books are, because it's compressing it. And so then the trick is, or a trick that the problem we're trying to figure out is like, well, how much does it get deformed then? What's the deformed? You know, so you kind of imagine this sphere on top of this. And so now we have some kind of deformed element to this thing. And how do you go about even calculating that? So one method that you can do, okay, first is we're just maybe trying to do a simulation for each of these systems, like the particle simulation. It's kind of Lagrangian, and just kind of treat each of these as a particle, and then you simulate a spring in between each one. All right. Then the next approach would be, well, what if you have a solid object like this, where you have like foam or some kind of compression, or maybe you got like some kind of tree model. And what if it's made out of rubber, or you decide, hey, I'm going to hang an ornament on it. Well, how much does the tree bend? All right. So the question is, how are you going to, so I don't know. What are some ideas? How might we want to solve that problem?
The tree one.
Sure. Tree one. I think it's in the same boat as the cube. The cube is simpler to think about because it's convex, I think. But how are we going to solve that in terms of the tree limb?
Seems harder than the cube because it's more of a torque thing than just a straight spring. If you apply a spring calculation to the rotation.
Yeah, I think you can. We're gonna be getting into some like tensor math and some rigid body stuff, but before we even figure out, we'll just use the physics function as a black box right now. But the thing is, how could we approach this problem? And maybe we could use what we've learned in fluids to kind of help us along. But how could we approach the problem so we could actually get to the point where that is realistic, that we can actually do that? Assuming we know how to solve the physics problem.
I think that would break it into bones. And then have some elasticity of the bone itself and the connection points, I guess. So depending on where you hang the ornament would change whatever calculation of how much torque is being applied to the bone.
Okay, so
Leverage that.
And hand waving.
okay, so in other words, maybe we might be able to transform this so that it's more like some kind of structure.
So we almost need a spring that, not a stretchy spring, but a rotating spring.
Right.
It has a point where that it wants to be at, and its angle relative to the points.
Points are all attached to a fixed point, and then when you put the thing on it, it pulls it away from the fixed point.
Right.
And then if you took the weight off, it would snap back to the fixed point.
Yeah, that's so that is one approach. Try to make a simplified model, and then we could just use the bones to affect the geometry on the.
However much resolution you want is basically how many vertices and edges you're going to have.
So you could rig it with a skeleton structure. So I think that's an excellent idea. Okay. Now, what happens though if the ball is too heavy and the tree is too strong, and we want to maybe simulate a tear?
Import other scripts.
Well, I mean, if we want a gradual tear, that means that our underlying mesh needs to be more complicated. Like it needs more layers. If we want to, do a total thing, that we need to be able to either break these limbs or, separate at a given point.
Yeah. So there is one technique that's commonly used called finite element method. Anybody heard the term finite element method? No? Some have, some haven't. For those who have heard about it, what's your short description? Like you're telling your mom how finite element method works. What's the short way of saying what that is?
Assuming mom isn't a doctor.
Right. Yeah.
See, now I have to explain the word discrete because I can't think of a way to explain it other than the word discrete. I mean, it's chopping it up into unknown number of parts and analyzing each of those subunits, right?
Yeah, I like it. It's a good stat. Okay, so finite element method.
It literally renders something that's really complex and better to finite elements.
So the idea here is you could take this and maybe even turn it into a giant mesh of components, and maybe they get too big. And then what you do, just kind of like over here, is you can kind of model this one. We only have to model what's happening between these guys, and you basically can kind of do it at a local level. But then you have to give it some time for things to propagate. In other words, if we hang something on here, eventually this whole thing might want to bend to the side. So you might have to give it time to propagate, or figure out what is the effect of this force going to be on the other parts, if for any particular change. Okay, so let's go over here and yeah, and the thing is, they all have very similar things because they're basically solutions for partial differential equations.
Finite element method like uses like a drawing style where you use your points to represent your entire things.
We have
Some familiar discrete element methods that you would install where like you have a ton of
Let's see here. This was done a year ago. I'm just looking for an example of, So, by splitting up. Now, I can't tell if that's the collision detection. See, sometimes the ear, if you noticed, who noticed that the ears were sometimes going right.
Well, things it doesn't have a real surface.
Yeah.
Like its appearance of the surface is into the.
But sometimes you have to be on the lookout. You put your scout goggles on to find out. Okay.
Oh, there we go. Yeah, I didn't notice it.
You don't notice it, and sometimes it's a case of you're doing an animation project, and you're like, well, it works. Except for that one time. So hopefully you have it set up so that if you need it, you can animate it out. Okay, so there's the idea there. Here's a solid dynamics. This can be. Sometimes they'll use. SPH, smooth particle hydrodynamics, as well, because you could take the particle approach to the whole thing. So this is kind of taking a particle approach to it. So you see all the spheres.
And that's how it was the stress on it at the time.
Right.
Okay.
So they're using that to visualize it.
Oh, cool.
Yeah. So there's another way to do it. You use SPH. So yeah, it's just like all the fluid stuff seems to come in handy here. It's just a matter of how do you determine the right equations to use. Okay. And you could use that to do thin shells on top of objects. Let's see here. Mesh rotation. Cell fracture. This is another thing you can do sometimes. You can kind of use it to model where the cracks should happen, I apologize. I'm going to mute it. And so over here, they're using, some method of essentially finding out which areas are maybe the weakest areas I don't know if they're voxelizing it. It doesn't look like they're voxelizing this, but you could use their voxelized approaches as well to kind of simulate rubber and things like that. I think what this is doing is just using kind of fractals to kind of determine how it should like break apart, you know? So let's hear. Let's find a.
Did they ever show it?
It's challenging to do that. Okay. Anyways, so we're it's 1 o'clock. So hopefully you learned a little bit. I try to be more practical, like how we program this stuff. But I think it'd be interesting to maybe get some particles like together and see what happens if we simulate the spring effect on the particles. I'd be worried that it's gonna like want to take off.
So like Source Forge, I think it was, like when we did finite element like meshes like this. Yeah, stability was questionable.
There's stability, but if you have like 2 points in space, is it gonna like spring off and just, you know? So we're gonna have to tie that into our boundary conditions where we say they are not allowed to leave, you know, and maybe it'll like bounce off the edges or something. But I'm curious to see if we can connect 2 particles together with a spring and then see what happens. Just let it go inside of the our little square grid.
It might help if you assign the distances to be the restoration distance to your starting distance, because that way you know it starts in a stable state.
Yeah. Okay. So this Sunday, it's going to be a student's choice homework. So as opposed to fluid, because I still feel like we're talking about that, the fluid stuff. So.
Can we do the fluid stuff, or would you rather we wait for another homework?
Yeah, I mean, I'm not going to stop you, but we'll just kind of make it the student's choice type thing. So, what's that?
The same parameters as last time.
Yeah. Just so yeah, that should be good.
Do you have a moment from semester, or do you have to go to the university yours?
I think we're going to stream the state of the university thing, but I do have a moment. So,
Okay.
Well, we're gonna stream it in here.
what's that?
We're gonna stream it in here.
I don't know if we're doing the exam or.
There's no senior seminar topics. There's state of the university for us.
Are they streaming it online?
I believe so. Yeah.